Hey guys, today we are going to talk about gauge theory. Gauge theory is a pretty important aspect of the standard model, so it's pretty important to get some sort of understanding of it before learning quantum field theory in more depth. So let's begin. So, what is gauge theory? Gauge theory is essentially the study of gauge transformations in what are called gauges. So to understand gauges, you have to talk about coordinate transformations. So say we have some function phi of x equals x. This means that phi of 1 is going to be equal to 1, and phi of 4 is going to be equal to 4. So far, so good. Say we have some new coordinate transformation where x equals the square root of x tilde. So what we have here is a coordinate transformation between two variables x and x tilde. This means that phi of x tilde is going to be equal to the square root of x tilde. This means that phi of 1 is still going to be equal to 1, but phi of 4 is going to be equal to 2. So our value for phi of 4 changes depending on the coordinates that we choose to use. Keep this in mind. So say we want to compare two different field values. Say we want to compare phi 4 and phi 2. So to compare two field values, we would have to subtract their values, right? So the distance between phi 4 and phi 2 will be phi of 4 minus phi of 2. Now phi of 2 is just going to be equal to 2, right? So phi of 2 is equal to 2. Actually, let's use a different, a more nicer value, because we get the square root of 2 in our new system. So let's actually use phi of 9 and phi of 4. So let's say we want to compare phi of 9 and phi of 4. So phi of 9 is going to be equal to 9 in our old system. So let's call this d old. It's phi of 9 minus phi of 4. That's going to be equal to 9 minus 4, which just equals 5. What about our new coordinate system? In our new coordinate system, phi of 9 is going to be equal to the square root of 9, which is 3. And phi of 4 is the square root of 4, which is 2. So we get 1. So comparing two values in our new coordinate system will also be different as well, as expected. Now this is a slight problem. It's pretty subtle. Say we want to compare again phi of 9 and phi of 4. So we want to compare phi of 9 and phi of 4 again. And say we actually know for certain that phi of 4 is the value in the old coordinate system. But say we don't know whether or not phi of 9 is being measured in the new system or the old system. Say we don't know what system phi of 9 is being measured in. This makes the statement phi of 9 minus phi of 4 pretty ambiguous. So to solve this problem, we introduce gauge theory. So we want to compare again phi of 9 and phi of 4. So the distance between, let's just use this new notation, 9 and 4. Where this just means the distance between phi of 9 and phi of 4. That's going to be equal to, again, phi of 9 minus phi of 4. But now we subtract it by some constant a. And we call this constant, we call that a gauge. Now, if phi of 9 is in the same coordinate system as phi of 4, then that means our gauge will be 0, since we would just have 9 minus 4, which equals 5. But if phi of 9 it was in a new coordinate system, we would then have 3, since phi of 9 would be 3 in the new system, minus 4, since again phi of 4 is being measured in the old system, and this value would be negative 1. So our first value for the distance between phi of 9 and phi of 4, that was 5, right? So we had phi of 9 minus phi of 4, and we found that to be equal to 5, since 9 minus 4 is 5. So this means that this minus a term has to be equal to minus 6. Because minus 1 minus minus 6 is the same as minus 1 plus 6, which equals 5. So by setting a to be minus 6, that will correct our problem and allow us to still get the same value even when we change our coordinates. So we can view a as a connection that connects the old coordinate system to the new coordinate system, since it's going to counteract the value of the field that is offsetted by a coordinate transformation. We can generalize this concept in 3 dimensions to get this formula that you see right over here. So in 3 dimensions, we see that this a constant is now a vector. So our gauge is now a vector where we have 3 components, a1, a2, and a3. And our gauge is a vector since we now have 3 dimensions. So we can have a gauge in the x direction, a gauge in the y direction, and a gauge in the z direction. So what we can do now is we can define some new quantity. Let's call this new quantity d prime, where d prime is going to be defined as phi of n plus ei minus phi of n over ei minus a n I. So this is the new quantity d prime. Now what we can now do is we can take the limits of d prime as ei approaches the 0 vector. And that's going to be equal to the limit as ei approaches 0 of phi of n plus ei minus phi of n over ei. Let's just consider just this part for now. Let's consider just this part. So you're not going to consider the gauge for now. The limits of d prime is going to be equal to this that you see over here. And that's just the definition for partial derivative of phi. So partial I phi. So this means that if we take the limit as ei approaches 0, this whole expression will just be equal to the partial derivative of phi with respect to some direction. So now we would have, say, now we could define a new quantity. Let's call this new quantity d, where d is going to be equal to partial I phi minus our gauge, which is a n I. Okay? So again, all we did here was we divided this term by ei, took that limit of that term, and that gave us this new quantity, partial I phi minus our gauge. Now, we know that spacetime is 4-dimensional, so we can just change our dimensions from 3D to 4D now. And our notation for 4 dimensions is we use mu instead of I. So we change I to mu, where mu takes on values of 0, 1, 2, and 3. I think that it should be 1, 2, 3, and 4, but most people use 0, 1, 2, and 3 for some reason. So we'll just stick with that for this video. So now we'd have d mu of x mu. Here we had di of n, but here we'd have d mu of x mu equals partial I phi, not I, mu, partial mu phi minus a mu of x mu. So when we switch from 3D to 4D, the x becomes an x mu, the I becomes a mu, and that's how we get this formula right over here. All we have is 4D instead of 3D. And this big D has a special name, by the way. It's called the covariant derivative. The covariant derivative. And we see that if this a mu term is 0, then the covariant derivative is the same as the partial derivative of phi. All right. Now, those that know differential geometry might be thinking that, hey, this covariant derivative implies that the field space is curved. And here's an example. So basically, here's a brief rundown of differential geometry. In differential geometry, when our coordinate system or space is curved, we switch from the normal partial derivative to the covariant derivative. So we switch from partial mu to what's called nabla, or this nabla is the covariant derivative in differential geometry if our space is curved. So here is our space is curved. So since we are using the covariant derivative here, it implies that our field space, which is the space that the fields exist on, is curved. Now don't confuse the field space for space-time. Space-time here isn't curved. The field space is curved. The field space is a mathematical space where the fields live in. So by using the covariant derivative, this implies that our field space is actually being curved. And we can evaluate this new geometric interpretation much further to get some pretty cool insights here. But first of all, before we do that, you might notice that this A mu looks like the EM potential. And that's because it is the EM potential. The electromagnetic potential is a gauge field. It's actually just a gauge, a physical gauge field, if you will. That's dynamical. That's what I mean. That's what I mean by physical. So the EM potential is a gauge field, and yeah, that's a pretty cool insight. And again, we can evaluate what it means for the field space to be curved. So for curved spaces, like a sphere, so here's a sphere, a poorly drawn sphere. Say we have some region on a sphere, some closed loop on the sphere. And then we have some vector from this closed loop. And say we want to take this vector and just transport it around a loop. If we actually do that through a method called parallel transport, our vector will actually look different if we parallel transport it in a loop. So try this yourself. Like take a basketball or something, take a vector on the ball, move it in a loop, and the vector you get where you started is going to be at a different orientation from the first vector, meaning that our space is curved. This is just like in gauge theory, where comparing two different points in our coordinate system, we'd have to use a gauge to connect those 2 points, because 2 different points can have different values if we change our coordinate system. And that's a similar thing that's happening here. We got the old vector back from the new vector, we would have to subtract it by some separation vector. And that's similar to what the gauge does, right? We subtract the difference between the field values by a gauge to get that old value back. That's just like what we do for curved spaces. So we can interpret this gauge here as indicating that our field space is curved. And in fact, the gauge A mu x mu is actually analogous to what's called the Christoffel symbols in differential geometry, which tell us the rates of change of our basis vectors along a manifold. And it turns out that the curvature for our field space, called the Riemann curvature tensor, is going to actually be the Faraday tensor, where f mu of x mu is going to be equal to partial mu a nu of x mu minus partial nu of a mu of x mu. So this is called the Riemann curvature tensor, which tells us how curved our space is. And the curvature tensor is actually the Faraday tensor. So the EM field, like the actual electromagnetic field, tells us how curved our field space is. And then the EM potential, the electromagnetic vector potential, tells us how strong the curvature of our manifold is, since our curvature will depend on the EM potential. And the EM potential is also it could be thought of as the Christoffel symbols. Now, if you don't know any differential geometry, what I said might not make any sense, and that's perfectly fine. It's completely okay if you don't understand what I just said. The truth is, we don't actually need to use that much differential geometry to understand quantum field theory. It's nice to know differential geometry in quantum field theory, but it's not necessary. So if you don't understand what I just said, don't worry that much. We're not going to use this concept that much in QFT and the standard model, but it's a pretty nice geometrical picture of what gauge theory means. If our gauge is non-zero, we can think of our field space as being curved, which is a pretty cool concept, and we can actually use this concept to motivate some other things, especially in quantum chromodynamics. But that's a story for next time. So, yeah, and it turns out that we can use this covariant derivative even more to connect different fields together, and I'll show you guys what that means right now. So here's our Klein-Gordon equation. Partial mu plus m squared phi. That's our Klein-Gordon equation. And we should already be familiar with the Klein-Gordon equation. But that's the equation in flat field space, right? We know that in curved field space, we have to change this partial mu to the covariant derivative. So in curved field space, where our gauge is non-zero, we should instead use big D mu plus m squared phi equals 0 for our Klein-Gordon equation. Now, in quantum field theory, we slightly changed the meaning of big D. So we found that big D was equal to partial mu phi minus a mu x mu. But in quantum field theory, we changed big D slightly, and we define big D as being partial mu minus i.e. a mu x mu. So we just remove the field from there. And then this E here is the QED coupling constant, also known as the electric charge. So here's our covariant derivative for QFT, or better said, QED. So all we do here is we'd actually just plug in our covariant derivative into the Klein-Gordon equation in curved space. And that will give us an equation that relates the free scalar field. Well, it's not really free anymore, but it relates the scalar field to the EM vector potential. And that's super cool, since by doing this, we are able to describe interactions between photons in particles like the Higgs boson and pions that are described by the free scalar field. So by using the covariant derivative, we are able to relate to the free scalar field and the EM potential, and we can describe interactions between them. We can do the same thing for the Dirac equation. The Dirac equation in flat field space is I gamma mu partial mu minus m psi equals 0, where the psi is just a spinor field. Again, we can just change up partial mu for the covariant derivative, and we get I gamma mu d mu, big D mu, minus m psi equals 0. And since d mu equals partial mu minus I e a mu of x mu, we can just plug that in and plug this in, and we would get an equation that relates the spinor field to the EM potential. Now the spinor field, well, we can consider the electron field, since the electron field is a spinor field. So we can consider the electron fields specifically, and then we can consider the photon field, which is just the EM field again. And this new equation, by plugging the cov derivative into the Dirac equation, we get an equation that describes the interactions between the spinor field and the vector gauge field, or better said, we get interactions between electrons and photons. And this equation is the cornerstone for quantum electrodynamics. This equation allows us to describe how electrons interact with light and how charged particles interact electromagnetically. So it's a pretty big thing. By using gauge theory alone, we are able to derive an equation that describes how the spinor field and the EM field interact with each other, and therefore describes how charged particles interact with each other. That's a pretty cool thing. And that's gauge theory. It's a pretty powerful tool in quantum field theory. We can also talk about things called gauge symmetries. We can talk about many things that relate to gauge theory, like the Higgs mechanism, for example. All those things use gauge theory. So gauge theory is a pretty cool concept that's pretty ubiquitous and versatile in the standard model. And yeah, that's how gauge theory works. Thanks for watching. See you guys another time. Bye.